We're going to move now from light reflecting off of surfaces such as mirrors to where light is actually traveling through a boundary to a new medium. And in that case, we're going to deal with refraction, or the bending of light. We looked at refraction when we did our initial waves unit. Remember that refraction occurs, the bending of light occurs when light is traveling from one medium and crosses a boundary to a new medium. And it's going to either speed up or slow down depending on the density of the two media. If the density is different, then the speed of light will be different. So if we look at this diagram, we have our incident light ray in one medium coming up to a boundary. When it hits the boundary, it will either speed up or slow down depending on the density of the new medium compared to that of the old medium. If the medium is more dense, then the light will slow down and it will bend towards the normal. If the medium that it's entering is less dense than the original medium, then the light ray will speed up and it will bend away from the normal. Let's take a look at a new situation where we have a light ray coming in. So here's our incident light ray, and it hits a boundary. Let's put some normals in at our boundary so that we can see where our angles of incidence and refraction are. So our angle of incidence is right there. Our light enters the material and the light bends. Is the block material more dense or less dense than the material the light is coming from? I'll let you think about it. I'll let you write down an answer. Pause the video, have everybody's answer checked, and then when everybody's answer is checked, you can start up the video again. All right, hopefully everybody figured out that it is slowing down because it's bending towards the normal, and so this is a more dense medium. Our angle of incidence is there. Here is our angle of refraction. Here is where it's bending. If we look down at the bottom, we have two more angles. We have an angle of incidence at this boundary, and we have an angle of reflection. Make the reflection a capital R for this unit. Those two are equal. So within the block, the light is hitting the boundary. Some of it is reflecting. Some of it is not reflecting though. Some of it is leaving and going into yet another medium. This medium down here, here is our new angle of refraction to correlate with this angle of incidence. Is the new medium down here where the blue light ray is traveling through more dense or less dense than the block? Again, write down your answer, pause the video. When everybody's answer is checked, you can start the video up again. Since the light is bending away from the normal, this is going to be less dense, and the light is moving faster here. We have a larger angle of refraction compared to our angle of incidence. This light ray that is coming up towards this original boundary has an incident angle right here as it hits the boundary. It passes into the original medium, our very first medium, and again bends. Here's the angle of refraction for that. And notice that the refracting angle here is the same as the reflecting angle for our incident light ray. And so this reflecting light ray and this refracting light ray are parallel. We're going to look at something in the lab that you're going to be doing called the index of refraction, and the symbol is N. The index of refraction is a ratio. It is a ratio of C, and we learned C equals the speed of electromagnetic radiation in air and in a vacuum, and that value again is 3.0 times 10 to the positive 8th meters per second, divided by V, and V equals the speed of light in whatever material isn't air or a vacuum. Light travels slower in everything except air in a vacuum, so the number N is always going to be bigger than 1. N in a vacuum is 1, and since air, again, allows light to travel just about as fast as light travels in a vacuum, we're going to use the index of refraction for air as being 1. And light is pretty much going to be traveling from air into another medium or from a medium into air. So knowing that the index of refraction for air is 1 is a useful piece of information. The lab that you're going to be doing is working with Snell's law. Snell's law looks at the angles of incidence and refraction and the index of refraction and gives us this equation. So I can measure angle of incidence, I can measure angle of refraction, and as long as one of my media, either the incident media or the refracting media, is air, then it's easy for me to find the index of refraction for the other material. That's the form of Snell's law that we're going to be using for the lab. We're going to be measuring angle of incidence and angle of refraction using a protractor and creating some refracting light rays. There are two other forms of Snell's law that you might find useful to know, and they deal with wavelength and they deal with speed of light in various media. So one version of Snell's law that looks at wavelength is this one: index of refraction of my incident medium times the wavelength of light in my incident medium equals the index of refraction of my refracting medium, that which is bending the light, times the wavelength of light in my refracting medium. We can also write it in terms of the speed of light, so the index of refraction of light in my incident medium times the speed of light in my incident medium equals the index of refraction in my refracting medium times the speed of light in my refracting medium. We'll be using these equations in working through problems in worksheet 2. You'll be using the Snell's law equation to do your calculations for the index of refraction lab that you'll be working on Friday. When you start with the Snell's law lab, or the lab of index of refraction, you're going to be using either a plexiglass square or a glass square to start. And you're going to position it on a sheet of paper with lines on the side nearest to you and the side farthest from you. Pin A is close to you, pin B is away from you. If you're looking at it from a side view, you see pin A is close to you. There's a line along the edge of the glass, and pin B is on the opposite side of the glass. Notice there's a frosted edge and a clear edge for your glass. You want to be looking through the clear edge of the glass, otherwise you won't be able to see anything. You also want to get down so your eye level is with the glass, so you're looking through the glass, not above the glass. If you look here, you can see pin A near you on the left, and pin B is hard to see but is on the right side of the glass where this arrow is pointing. You want to eventually rotate this glass plate to get these pins lined up. This is starting the rotation. Pin A is close to you. Pin B is the middle one and is on the back side of the glass plate. Pin C is the far one, and eventually you want to have all three of these pins lined up while you look through the glass, not above but through, looking at the bottom of the pins. Now we have it rotated even more. Pin A again is closest to you. Pin B is almost directly behind pin A. That's what we want. Eventually we want pin C directly behind pin B, which is directly behind pin A. If we rotated this just a hair more counterclockwise, we would have all three pins lined up as we look through the glass. If you look above the glass, you'll see the pins are nowhere aligned with each other, or so they seem, but when we look through the glass, the bottom of each of the pins will be one behind the other. That's what we want. For the glass, you're going to be keeping pin A in position and moving pin B successively to the left, so you create multiple lines for refraction, so you can measure multiple angles of incidence and angles of refraction for your first square. For your second material, you'll do basically the same thing, but you will use a liquid, a bottle, or you will use a crystal.